Okay, so we're back to factorising. I've got our cubic expression, so we use our cubic knowledge in reality to factorise. So we try and find a 0 of the polynomial. 1, 1, 10, so 1's not going to work. As it turns out, -2 works and gives me a 0. As opposed to doing a division, I've decided to use a repeated factor method. We could use synthetic. So I've used my repeated factor method. So what do I multiply the z by to get a z cubed? Well, that would be z squared. Multiply the z squared through, I get a 2z squared. I've got 2z squared, I'm meant to end up with a negative z squared, so I've got to subtract 3 of them. Multiply that through, that gives me a -6z. It's meant to be negative z. So I add 5, and yeah, so hopefully we've got that worked out. So once you get down to your quadratic expression, our expression there is factored, isn't it? Now I've cheated a little bit, I guess you could argue, that I've decided to leave it as a quadratic expression and not completely factorise it. To factorise from there, we're going back to our quadratic processes, and we might complete the square on that. Okay. B, I guess always with our cubics for methods and specialists, always look to see if there's the opportunity to group. And the coefficients in this case of 1, -i, -4, their product is 4i, which suggests that you will be able to group the terms, and that's what we've done. Okay, so we've taken z squared out the front and got a z minus I. Take a -4 out the front, get a z minus I, end up with a z squared minus 4z minus I. Factorise that z squared minus 4, and there's my 3 linear factors. If we have higher, to be honest, more often than not, we're looking to solve, and we're probably going to use a de Beauvoir's theorem. If by chance we do have something like a 4 or a 6, and I've never seen it on an exam one, we're going to use our cubic expansion typically. So you're not necessarily going to remember this expansion rule, okay? But instead, you're going to remember that you can apply a difference of squares twice. Or if I've got 6's, I can convert it into a difference of squares again. All right. So if we do that up here, there's my z to the 4 minus 81, which is z to the 4 minus 3 to the 4, which is z squared squared minus 3 squared squared. So I can apply my difference of squares, z squared minus 3, z squared plus 3. Obviously, I've got a difference of squares again. And then if I introduce my I and make it minus 3i squared, I get another difference of squares. All right. Similarly, for z to the 6, I'm going to treat that as z cubed squared minus 1 cubed squared. So it's a difference of squares. Z cubed minus 1, z cubed plus 1. And now we've got a difference of cubes. So z minus 1 plus plus z squared z1, z plus 1. And then we get our z squared minus z plus 1. So it's just trying to remember that cubic expansion. Difference of cubes, difference of squares are really significant. But as I said, very, very rarely would that ever come up in a tech-free environment. Maybe a SAC, but not an exam. All right, which leads us through, I guess, into that fundamental theorem of algebra, which basically says if we have a sum of factors, P of z equal to 0, P of z equal to 0, and it has degree n, well, it'll have n roots or n solutions, but they may not be distinct or different. So I guess a really simple example is something like x minus 1 squared is equal to 0. Well, it's a degree 2 polynomial, but it's only got one solution. It's got a repeated solution, so only one distinct solution. So it may have up to as many as n distinct solutions. You can get the n linear factors, but again, they're not necessarily non-repeated factors. All right, so it's really just from here, just a continuation from our factorising. So z squared minus 2z plus 5, how do we solve any quadratic expression? We can complete the square, we can use a quadratic formula. And in this case, I've completed the square. And we get our 1 plus or minus 2i. Again, note, all real coefficients, conjugate pair. All right. Z cubed plus all real coefficients, so it will be a conjugate pair. But how do we solve? Well, let's get my first solution. I've gone for a p of -1 and then factorise it or do a division. So instead of doing a division, I've decided to do a synthetic division. So I end up with my x squared plus 2x plus 5. Same sort of thing, I've got to solve the equation. So I get my z equal to -1. I've now got to solve that quadratic expression equal to 0, complete the square on it, introduce my I term, and I get my -1 plus or minus 2i, my conjugate pair. Yeah. Example 14, find the roots of the equation given that z minus 2 minus I is one solution. Okay, so if that is one solution, it means, since they're all real coefficients, that the conjugate is also a solution. So minus 2 plus I is a solution. So I want to write them in factored form. All right, so minus 2 minus I guess as a factor, what I'm really saying is that's the same as z minus 2 minus I and z minus 2 plus I, my two solutions. So if I do that, means then that becomes z plus 2 plus I, z plus 2 minus I. If I expand those, just do your standard expansion and treat it as a little bit like z plus 2 all squared. So I get my z squared, I get my two lots of 2z, except instead of 1, and sorry, z plus 2, I get my plus 4, z plus 2 squared, but I also end up with an I squared. So what you'll find is, whenever you multiply those together, you'll get what looks like your normal standard quadratic expansion plus the I component. So if I want to do, for example, sorry, it's not rubbing out for me. If I want to do a z plus 3 minus 2i, z plus 3 plus 2i, well, I'm going to have my z squared term, 3 plus 6z plus 9, but I also have a minus 4i squared expression. All the I stuff will cancel. Yeah, so you can check that. That'll come to 6 squared plus 6z plus 13, all right, as a full expansion. So you may not need to do the full expand everything out as I've done there, but you know, if you do, it's what's an extra minute, it'll be okay. So I end up with my z squared plus 4z plus 5. That's one factor. Okay, and I know because it's a cubic, I've got another linear factor there somewhere. So az plus b. So instead of doing a division by z squared plus 4z plus 5, what if I just do an equating? If I was to expand this bracket, I'd get az times z squared, and that would be giving me az cubed, and that would be the only z cubed expression. All right, and that's got to equal the original function, which is just 1z cubed. So az cubed will equal z cubed. Similarly, in the constant, I'll end up with b times 5. That's the only constant expression that I can get. So that 5b has to equal the constant of the original expression, which was also 5. So just from equating really simply, I can get a and b is equal to 1, which means my other factor is going to be z plus 1, which will give me a z minus 1 as a solution. So then there's my 3 solutions. So I think that's just such a nice little approach instead of having to do another long division or doing a long division with z squared plus 4z plus 5. All right, one to go. Show that 2 minus I is a solution to that expression. Okay, so obviously if it's a solution, if we substitute it in, we'll get a true statement, which in this case it'll equal 0. So substitute 2 minus I into z cubed, I get 2 minus I all cubed. Substitute 2 minus I into z squared, I get 2 minus I all squared times 2 minus I. I've got a z, which is 2 minus I, and then I've got minus 2 plus I. So instead of expanding everything here, hopefully you can see fairly straight away, I've got my initial 2 minus I cubed. 2 minus I times 2 minus I squared is also 2 minus I cubed. 2 minus I, take a negative out the front, I get another 2 minus I. So each term cancels. So really easily there we see that 0 does equal 0, so it's true. All right, so given, I think the fact that we did the substitution and got a 0 so easily also suggests to me that maybe we can do a grouping. Because let's be honest, trying to do a division in this scenario would be next to impossible. You know, we might be able to, but what do you go with? With so many imaginary coefficients there, it's going to be a challenge. So in actual fact, what we needed to be able to see that if we took z squared out as a common factor of the first term, I get z minus 2 minus I. And then if I take a 1 out the front of the next term, I also get a z minus 2 minus I. So really for that one, it's actually very straightforward as long as you see the grouping that can take place. So z squared plus 1 out the front, that's going to give me plus or minus I as a solution. The other factor, or the other solution, 2 minus I, which is the one that was given to us. I guess it's worth noting that we don't have a conjugate pair. There's not necessarily. It's obviously 2 plus I is not a solution. So yeah, we don't always get conjugate pairs depending upon the nature of the polynomial we've got.